mathematics, because this is the Dean's Distinguished Visiting Professor lecture, which gives me a particular thrill because it's something that doesn't have my name on it, but it has the Dean's name on it, and it is going to be a very exciting lecture. So before we start, I do want to acknowledge that much of our work takes place in the traditional territory of the neutral Anishinaabe and Haudenosaunee people. Our main campus is situated on the Haldeman Tract, the land granted to the Six Nations, and includes 6 miles on each side of the Grand River. Our active work towards reconciliation takes place across all our campuses through research, learning, and teaching and community building, and is coordinated within our UW Office of Indigenous Relations. Our esteemed guest today, our esteemed guest today for today's lecture is Dr. Sanjeev Khanna, the Henry Salvatore Professor of Computer and Information Science at the University of Pennsylvania. Sanjeev received his PhD in computer science from Stanford University in 1995, spent 3 years as a researcher at Bell Labs before joining the University of Pennsylvania. He's an ACM fellow, a Guggenheim fellow, a Sloan fellow. I was going to make a joke about a jolly good fellow, but anyway, sorry. But amongst many other truly important accolades, and has received a number of awards for teaching as well. Sanjeev's primary area of interests are in approximation algorithms and hardness of approximation, combinatorial optimization, and sublinear algorithms. Today's talk is titled "The Sublinear Lens and the Matching Problem." And so I really am excited to see what this will be. And I do hope that over his time here, many of you have had a chance to work closely with him. So before getting on with Sanjeev's talk, I want to note a brief note about programming. We do hope you'll join us next door in the Fishbowl, DC 1301, after this lecture for a reception where we can enjoy some refreshments and have further discussions with Sanjeev. So without further ado, I'm pleased to present Sanjeev Khanna. Thank you.
Thank you for the kind introduction. I want to start by thanking the Faculty of Mathematics for giving me this opportunity to spend my sabbatical term here at Waterloo. And I also want to thank my colleagues here in the broader theory group who did the groundwork for making this visit possible. So when I decided to come to Waterloo for my sabbatical term, all I knew was this is a great CS department with a wonderful theory group, and that the winters in Waterloo can be a little bit intense. So all that is true. But during my visit, I discovered many other things. I discovered that Waterloo attracts some of the most intellectually engaged students that I have met anywhere. I have discovered the joys of starting and ending my workday with a quiet walk through the Waterloo Park, which I did almost every single day during my visit. I have discovered lots of cafes, and farmers markets and bakeries, which have made for fun weekends. So all in all, I've really enjoyed all aspects of my visit here. So thank you again for giving me this opportunity to spend this term here. So I'm going to talk about the sublinear lens and the matching problem. Since this is an end of the term talk, I'm going to keep this talk as a light survey talk, and it will revolve mostly around my own personal research history with this problem. Okay, so let me start by reminding everyone what is the matching problem. So a matching in a graph is a set of edges which has the property that every vertex in the graph has at most one edge incident on it. Okay, so in this graph, the red edges form a matching. And the goal in the matching problem is to find a matching of largest possible size. And once again, in this graph, these red edges form a matching of largest possible size. Okay. And the special case, when the matching has the property that every single vertex in the graph has an edge incident on it, is called a perfect matching. And it so happens the red edges here, they form a perfect matching. So while many of the results I will talk about would apply to matching problem in general graphs, some of the results will be specific to matching problem for bipartite graphs. And many of the interesting applications of the matching problem are already captured by the setting of bipartite graphs. So for example, you could model the problem of assigning jobs to machines based on compatibility constraints so as to do load balancing as a matching problem. You could also model the problem of assigning items to buyers so that every buyer receives an item that they are interested in as a matching problem. And you could also model advertisers and adverts matching pairing as a matching problem, which comes with several other bells and whistles on the side. So as you can imagine, this problem has a very long and rich history. And as early as 1930s, some of the structural results that we rely on were already discovered about this problem. Hall's theorem is a good example of one such result. And in terms of modern algorithmic history of the matching problem, one could perhaps say that for the bipartite matching, at least, it started with the work of Ford and Fulkerson in 1956. And then there was the seminal work of Edmonds in 1965, which tackled the general matching problem. And in fact, this paper of Edmonds is credited with highlighting the notion of polynomial time efficiency, which we have come to accept as, what formalizes what it means to perform computation efficiently. But then the list goes on, and of algorithmic results, there were a number of subsequent breakthroughs on this problem, including one as recent as 2022. The takeaway from all this is that after 100 years of research on this problem, new developments still keep happening, and we are not done yet with that. And I think this is a testament to the central place this problem holds in optimization. So this talk is going to be about the following question: can we design sublinear algorithms for matching problem? Okay. So why we care about designing these sublinear algorithms? So let me start by briefly motivating it, and then I will formally define what I mean by these sublinear algorithms. Okay. So here are some problems that we know how to solve efficiently in the classical sense. I could ask you to compute page rank in a recommendation system of nodes which are participating in, or the entities that are participating in the recommendation system, or simple problems like find average degree of a node in a graph, or find number of distinct values in an array. All these problems we know how to solve efficiently in the classical sense, where you have complete random access to the input. And we are happy if we have an algorithm which runs in close to linear time. Okay. But now look at these same computations on some real-world data sets. Suppose I ask you to compute page rank of web pages on the entire web graph, or I ask you to find average number of friends in a large social network like Facebook, or I ask you to identify number of unique daily visitors to Amazon, for example. And suddenly, if we start to look at data sets of these sizes, the traditional gold standard of algorithmic efficiency, which has been linear time and linear space, that no longer seems to be sufficient. And this is what has motivated the study of sublinear algorithms over the last 2 decades in particular. Okay, it's older than that, but the last 2 decades is when a lot of the interesting developments have happened. So in this talk, I'm going to look at 2 particular kinds of sublinear algorithms. And the first one is the notion of sublinear time algorithms. And here, the model is that the algorithm has random access to the entire input. But we want to design algorithms which are going to do global computations on the input without reading the entire input even once. And when I say not even once, don't think it's like I'll read 10% of it. No, you want to do computations by looking at a negligible fraction of the entire input. Okay. So some problems that I've already alluded to, mentioned earlier, which people have studied in this setting are here. So for example, you could find pages of large page rank in sublinear time on the web graph using sublinear time algorithms. The second model that I will talk about, it's a model of sublinear space algorithms that's called the streaming model of computation. And this was put forward only in 1996. And the goal here is that the data is going to be revealed to you as a stream. So for our particular application of a graph problem like matching, you should think about that the graph is going to be revealed to you as a sequence of edges, and you're going to see these edges pass by. You have limited memory to store information about what you are seeing passing by. And the goal is to design an algorithm that takes this limited snapshot of the data that passes by and solves a global problem on it. Okay. So that's the streaming model of computation. And then again, some examples of problems that people have studied how to solve efficiently in this setting are here. So for example, if you look at the stream of IP accesses that Amazon has on any given particular day, you can estimate close to an optimal answer that is with very high accuracy, how many distinct or how many unique visitors Amazon saw on any given day, using a memory which is not much larger than the memory you would need to simply write down the answer, okay? Even though this stream of accesses may run into tens of millions. Okay, so, at the first glance, it's going to seem like these goals or these desires to have sublinear and time and space algorithms, this is going to be a big restriction, big computational restriction, and we should not be able to do too many non-trivial things when our hands are so tight. But the last 2 decades have shown you can in fact solve a variety of non-trivial problems very efficiently in sublinear time and in sublinear space. And more interestingly, to me personally, revisiting classical problems that we thought we have solved, we have understood fully because we had already linear time and space algorithms for them. Revisiting these problems from the lens of sublinear computation have led to discovery of very exciting new algorithms and also new connections, which at first glance seem extremely surprising. And in fact, my own research transition into the world of sublinear algorithms started with the work on the matching problem some 15 odd years ago. So the rest of this talk is going to be arranged in 2 parts. And the first part, I will talk about sublinear time algorithms for the matching problem, what we know about this. And then the second part will be on sublinear space algorithms for the matching problem. Okay, so let me set the context and for how it all started for me, my work on the matching problem. So the year is 2008. And the context is, okay, maybe this is not the right context for this work. So let me set up the right context. I might have accidentally traumatized some young people in the audience who have only known the stock market to always go up. Sometimes it does go down. Okay, so the year is 2008. And at this point, my research since my PhD years has been completely focused on the area of approximation algorithms for NP-hard problems. Okay? So these are problems for which the exact algorithms take exponential time, and you're very happy to come up with a polynomial time algorithm that can compute an approximate solution. Okay? So at this point, my view of an efficient algorithm is an algorithm that runs in n to the order 1 time. And as you might have noticed, the O notation appears in the exponent. Okay, so it's that's what I think of as an efficient algorithm at that point in time, because we're working on NP-hard problems, and your comparison point is exponential time. So this is all that you need to be efficient. And it's around this time, a colleague, Ashish Goyal, who's been my long-time collaborators, suggested that we work on the following problem, and the problem being this: given a regular bipartite graph, can we find a perfect matching in a regular bipartite graph in time that's much faster than reading the graph even once? Okay. So let's look into this problem a bit more closely. So what's a regular bipartite graph? It's a bipartite graph where all vertex degrees are the same. Okay. And it's a well-known fact that every regular bipartite graph has a perfect matching. Okay. So if you wanted to know what is the size of an optimal matching, that is done. You just know it because it's a regular bipartite graph. The challenge is, can you find one such matching? Okay. Okay, and why was he interested in this problem? He arrived at this question because of some routing questions that he was looking at, and indeed, this problem comes up in scheduling and routing. But it's also actually, more interestingly, a key subroutine in solving the edge coloring problem in general bipartite graphs, where this problem is a subroutine along the way. And for those of you who are familiar with Birkhoff von Neumann decomposition of doubly stochastic matrices, this problem is also closely related to finding such a decomposition. Okay, okay, so I asked, so what do we know about it, right? And so let's set up some notation. N is the number of vertices, M is the number of edges, and D is going to be degree of each vertex in the graph. And there is a long history of works. I'm writing here only the last part of this history, which is relevant to us. And so in 1982, we already had an algorithm for this problem, which ran in essentially linear time. It ran in order m log m time. And then around the same time, Gabor and Karev figured out a very cute way of solving the problem in order m time when D is a power of 2, when the degree happens to be a power of 2. It took 20 more years to get rid of that power of 2 assumption and get an unconditional order m time algorithm for this problem. But in 2001, we had what looked like the dream result for the problem. In the time it takes you to read the entire graph once, you can just output a perfect matching in this graph, okay? So, but the question we wanted to look at is, can you go below order m time? Okay, so at this point, it would be useful to make the excess model entirely clear, since we are talking about sublinear time going below even the time it takes to read the graph. So we're going to assume the graph is given to you as an adjacency array. This is just like the adjacency list representation. Instead of linked lists, I'm using arrays to represent the neighbors of each vertex. So in particular, for each vertex V, I'm going to assume we have an array, A sub V of size T. If I look at the ith entry of this array, it just tells me the name of the ith neighbor of this vertex V. Okay? No assumptions on the ordering of these vertices. An adversary could have arranged how the neighbors are arranged in each one of these arrays. Okay? Good. So that's the model. And we started with really the first thing that one would think of, if you wanted to go below linear time. Could we just somehow try sampling the edges in this graph? So generate a sparse sample, hope that it still has a perfect matching surviving in it, and then run a fast bipartite matching algorithm on this sparse sample. Okay. Usually, sampling is not a good strategy for recovering an exact solution. Okay. It's a good strategy for recovering an estimate or recovering an approximate solution, but not an exact solution. But to our surprise, this problem turned out to have enough structure that we could get an algorithm that runs in n to the 1.75 time and solves this problem. So this is only interesting when the graph is dense. But what this result is saying is, if your graph has maybe even omega n square edges, I can solve it in n to the 1.75 time. So it's a truly sublinear algorithm once the graph becomes sufficiently dense. Okay. So we pushed on these ideas more and more, and ultimately we thought we had our dream result for this problem. We came up with an algorithm which could solve this problem in n to the 1.5 time. And this just seemed like, the right answer to us. And you can formally show there are barriers to taking any sampling-based approach beyond this n to the 1.5 time. But while we could formally prove that those things as barriers for sampling-based approaches, we could never turn them into lower bound results that prevent all algorithms from going below n to the 1.5 time. And it turned out that was happening for a good reason, because out there was an even better algorithm, and which has a very surprisingly simple structure. Okay, so I want to tell you about this algorithm and a little bit about what happens in it. Okay, so high-level structure of this algorithm is going to be this very simple two-line thing. I'll initialize M to be an empty set, and M is going to be my final matching at the end. So at the end, it's going to be a perfect matching. And the algorithm will just follow the following strategy. As long as M is not a maximum matching, it's going to find a way to increase the size of M by just one edge at a time. Okay, so baby steps to improve the solution, and I'll keep improving it until I'll have my perfect matching.
You're not playing any games to have the sample be vaguely close to regular.
No, there is no samples in this so far. This is a different algorithm.
But you're augmenting it by an edge.
I'm augmenting it by an edge. No, I have not explained that.
Fine.
Yes,
Fine.
yes, that's okay. Randomness will come in, but I've not explained yet how. Okay, good. So how do you increase a matching by one edge? Well, this is the classical approach that is the underpinning of most algorithms for matching. You find what's called an augmenting path. What's an augmenting path with respect to a matching? So you have some matching M, which may be suboptimal. An augmenting path is a path of odd length, which will start at an unmatched vertex in the graph and end at an unmatched vertex in the graph, and will alternate between non-matching and matching edges. So what's the property of this path? If I count the number of non-matching edges and I count the number of matching edges, then the number of non-matching edges is one more than the number of matching edges, because you start with a non-matching edge and you have odd length, okay? So it means if I flip the role of matching and non-matching edges, I will end up increasing my matching size by one. That's the nice thing about an augmenting path. So here is an example. These blue edges are my current matching. And those two red edges, which I'm highlighting, if I add them to the blue edge on the top, I'm going to get an augmenting path. It starts at the unmatched vertex at the lower left, goes to the blue vertex on the top right. You take the matching edge to come back to the top left blue vertex, and then take the red edge to go to the last unmatched vertex. Let's flip the roles. And what do we get? We get a matching of one size larger. Okay, so that's the notion of an augmenting path. And it's not difficult to show. M is a maximum matching if and only if it has no augmenting path. Okay, so this is a sound strategy for improving your solution. Okay, the only thing that's left is how does one find an augmenting path? Okay, so we are going to do this by forming what's called an augmentation graph. And this is standard. This is nothing new. This is how classical algorithms on matching, bipartite matching proceed. Okay. So what are we going to do? We're going to make a directed graph. And the start of this directed graph is we're going to add two new vertices, S and T. S will connect to every unmatched vertex on the left side, and every unmatched vertex on the right side will have an edge to T. And what's going to happen by the time I'm done explaining how this graph is constructed, that any S to T path in this graph would correspond to an augmenting path. Okay, and every augmenting path would appear as some S to T path in this graph. Okay, so that's going to be the goal of this graph. Okay, so how are we going to build this? So let's say P is the set of vertices on the left side, Q is the set of vertices on the right side, and M is the current matching. We're going to direct, if the graph is going to be directed, we're going to direct all the non-matching edges from P to Q, and we're going to contract every matching edge UV into a single vertex. Okay? And at this point, it's not at all difficult to show that any S to T path in this new graph is going to be alternating between non-matching and matching edges. Anytime you pass through the contracted vertex, you're going through a matching edge because of our construction design. And so any S to T path in this thing will be exactly an augmenting path. So the picture looks like this. Okay? This is how this new graph is going to look like. So nothing special so far. I'm really doing things like the standard matching algorithms. Okay. Now comes the interesting part. How do we find these augmenting paths? The matching algorithms would use complex data structures in general, do a lot of bookkeeping to find these augmenting paths efficiently, iteration after iteration, or find lots of them in some clever way. We are going to do something which looks on the surface completely silly. We're going to start at S and randomly wander out from S until we hit T. What do I mean? From S, look at the outgoing edges, pick one of them uniformly at random. Whichever vertex you arrive at, look at its outgoing edges, pick one of them uniformly at random. Keep doing this until you land at T. When you land at T, it's definitely an augmenting path. So if we follow this strategy, we will finish with the perfect matching because we will keep finding augmenting paths. The only suspense is how long does this entire process take, okay? And I want to highlight it's completely memoryless, okay? What happened to you in a previous iteration has no bearing on what you're going to do in this iteration, okay? And you don't try to remember, I have already seen this vertex, you do no bookkeeping whatsoever, okay? And here is the surprising thing that you can show. When there are k vertices that remain unmatched, the expected length of the augmenting path is roughly, not just roughly, it's actually, this is pretty much the right answer, n over k plus 1. So let's take a moment to understand what this is saying. In the beginning, all vertices are unmatched. It is saying it will be constant time to find an augmenting path. as more and more vertices get matched, towards the end, you have maybe just one vertex left unmatched. The time would increase to n at that time, but bulk of the journey is happening with this time being really small. Okay, there are no hidden constants. I really meant it to be n over k plus 1. Okay. Now, in general, random walks in directed graphs are very poorly behaved. You can easily construct a strongly connected graph where it will take exponential time to discover all the vertices. But somehow we are getting this dream scenario kind of a result. And so what happened here? The magic ingredient is for all vertices in the augmentation graph, we have the property that in degree equals out degree. And you can use this property to show that the random walks in this graph are going to be really well behaved. And in particular, the total time this algorithm will take is going to be just n ln n plus n. Okay? And that was quite a journey for someone like me, from using O notation in the exponent to even working out my constants in the runtime. Okay, it didn't last. Okay, but at least at this one moment it happened. So just to then summarize, you get an order n ln n time expected time algorithm to find a perfect matching in a regular bipartite graph, and this is really just a little bit more than the time you would need to write down the solution if I was dictating it to you. And this is expected time. You can turn, without blowing up the time, turn it into a high probability success probability algorithm. You can show that with probability 1 minus 1 over poly n, you can find a perfect matching in order n log n time. Okay, and we also were able to show that this is optimal. That is, if you wanted a high probability result, you can't get rid of log n. It seems like maybe one should go a step further, get rid of the log n also, but you can't as long as you require a high probability result. Okay. I want to mention a cute implication of this, and very useful implication of this result. There are many fast flow algorithms that are based on continuous techniques. And so when you run them even on integer capacity flow networks, they will output a fractional flow solution. Okay? But lots of the applications of flows start by, the textbook applications start by saying, let's assume we have an integral optimal solution. You could use this random walk idea, and it was used just a year later in this work of Lee, Rao, and Shrivastava, to turn any fractional flow solution, which you might have computed by any algorithm of your choice, into an integer valued solution of the same value in order m log m time. So in the time it takes you to read the flow network and the entire solution once, just a bit more time than that is enough to convert your fractional solution into an integral solution. And this is also very useful if you had a algorithm based on continuous techniques that gave you near optimal solution. Then after you turn it into an integral, you can just do a few more augmentations to make the solution optimal. Okay? And that's actually kind of how they used it in this particular work. Okay? And so what's the connection to the previous algorithm? Flow conservation means that incoming flow to each vertex equals outgoing flow. And you can really view this as in degree equal to out degree condition that the previous work utilized. Okay. Okay, so at this point, we started to think about what about the matching problems in general bipartite graphs, if not, general graphs, right? So we got this result, which, was surprising, and maybe we could carry, some ideas from here to get something interesting for general bipartite graphs as well. Okay. Unfortunately, things turn pessimistic, provably bad quickly. So just a few years ago, in the work with Sepper and Yu Chen, we observed that getting even a constant factor approximation to matching problem in general bipartite graphs requires omega n squared time. Okay, so even constant factor, which doesn't look like such an exciting outcome, would require basically in the worst case as much time as reading the entire graph. So you couldn't go below. You couldn't get a sublinear algorithm even if you settle for approximation. However, if instead of finding an approximate matching, we shift our focus to estimating the size of a largest matching, good things indeed happen. Okay. So let me tell you about this beautiful result of Sohail Benezat from just a couple of years ago. The result shows that give me a graph where the maximum degree is D. Then you can estimate the size of the largest matching in the graph to within factor of 2 in time, which is roughly order D. Okay. So if your graph doesn't have a very high degree, this is not just only sublinear in the size of the entire graph, it will be even sublinear in the number of vertices. Okay. It's a really remarkable result. You can easily construct graphs which all satisfy degree D bound, but their matching sizes differ by a factor of up to D. So this is a very non-trivial statement. Okay. And the work itself is based on another amazing paper from more than 10 years ago by Yoshida, Yamamoto, and Ito. And since the discovery of this result, it has been a key subroutine in many other sublinear algorithms, simply because matching problem appears in so many other problems as a subroutine. Okay? And this is an optimal result. Okay? That we knew, like if we could ever get a bound like this, this would be optimal. We have known that for quite some time. Okay, so in the remaining time, let me not go over the details of this. Let me switch gears and let me say a little bit about the other resource, the resource of space, and what do we know about the matching problem in the setting of sublinear space. Okay, so I want to remind you what is the setting now once again. The graph will be revealed to you as a stream or sequence of edges. Once an edge has been shown and it's gone by, if you didn't decide to remember information about this edge, there is no recourse. Okay, you lose random access to the graph in this model. So edges are shown once and then they go by. You have limited space. You decide what information you want to store as you see edges pass by. Okay, so one motivating example you can think of is that you have a very large graph that is stored in some slow disk, and as the disk spins, it shows you edges in the order they were stored on the disk, and your algorithm is running on your laptop. It can't store this entire graph, and it uses the laptop memory to store whatever information it wants to store and then compute with it. Yeah.
Do you know the number of nodes?
You can assume you know the number of nodes, and you can assume you also know the number of edges. Yeah. Many times, okay, sometimes it's not possible to erase, get rid of these assumptions, but many times at least assumptions about knowing the number of edges in the graph can be eliminated with a few more tricks. Okay, so this problem was already explored fairly well in a very influential paper by Feigenbaum et al. In 2005, where they looked at solving graph problems in the setting of small space. And they made two simple observations about this problem. The first one is, of course, there is a trivial algorithm which uses order n squared space for this problem, which is just going to store the entire graph. Okay? So that doesn't look like much of an observation you would want to highlight, except they proved if you wanted the exact matching solution, this is optimal. You can't do anything better than storing the entire graph. Okay? So this is, so you know, if you wanted to get sublinear space, you have to shift your focus on approximate matching. And then they also put forward an approximate matching algorithm that does save space. And the algorithm they proposed is to maintain maximal matching as the edges pass by in the stream. So what exactly are we doing? You are going to see an edge UV appear in the stream. You are maintaining a maximal matching solution. You check if in my solution U and V are both unmatched currently. If they are both unmatched, you add the edge UV to your solution. All you need is the space to store your solution. But your solution will never have more than n edges. So it will only take order n space. And then it's a well-known fact and very easy thing to show that any maximal matching is within a factor 2 of a maximum matching in a graph. So you just put these two things together and you get this half approximate matching. Okay? So then let me summarize what we learned from this paper, which explored, which was the first one to formally explore this problem. Exact solution in order n square space, and that's the right answer for exact solution. Half approximation in order n space. Okay. And the question, is can we find better than half approximate matching using small O of n square space? That is space which is better than storing the entire graph. Okay. And surely it seems the answer has got to be yes. That maximal matching algorithm, right? It's the first thing you will think of in a minute, right? And with just a little bit more algorithmic cleverness, we should be able to do much better. Okay? And that's exactly what we thought. And after a few years, we finally realized what we were up against. And we were up against a major open problem in graph theory. Okay? But the connection, it took many years for us to build up to that connection. So let me explain this connection because I think I think it's a really interesting connection. And now it doesn't look as surprising, but at that time it was quite surprising to us. Okay, so this connection is through what's called Roosa-Zemeredi graphs. And it's a really fascinating class of graphs. If you haven't seen them before, I think just this alone would be a good thing to kind of know about from this talk. Okay, so to define these graphs, I need to tell you about the concept of induced matching. What's an induced matching in a graph? It's a matching with the property that there are no other edges present among the vertices that are participating in this matching, okay? So these matching that I'm highlighting here is an induced matching. So if you look at the vertices connected by this matching, you can see the graph does not contain any other edges between them, okay? So what are Roosa-Zemeredi graphs, or I'll just call them RS graphs? These are graphs whose edges can be partitioned into large induced, edge disjoint induced matchings, okay? The keyword here is large, okay? So I'm looking at graphs whose edge set can be partitioned into large. Think about omega n size large, okay? That's my going to be my interest. Induced matching, okay? Good. And so here is an example of a RS graph whose edge set can be partitioned into 4 induced matchings of size 3 each. Here is one, another, and another. Every one of them is induced, okay? And try playing it with yourself. Try packing large induced matchings in a graph, and you will see it's going to be challenging very soon if the matchings are of size omega n. Why? Because each time I put in an omega n size matching, I forbid omega n square other edges from existing in the graph because of the induced property, okay? Okay, so let's define this quantity, Rs of n comma beta. It's the maximum number of edges an n vertex Rs graph can have if its edge set consists of induced matchings of size beta n, okay? And we proved the following result. Took us a few years. In fact, we had kind of discovered this result, but we just didn't know what such graphs were ever studied by anyone. They had a name and so on. We had identified an obstruction which had these properties, which RS graphs have, but we just didn't know anything about them. Okay. So anyway, so what is the result? The result is any streaming algorithm which gives better than 2/3 approximation to the matching problem will require space, which is at least the size of an RS graph, largest RS graph, that contains induced matchings of size roughly n over 4. Okay. Okay, so when we discovered even this, before we knew about RS graphs, we didn't think of this as a bad news at all, because how dense can such graphs be after all? Because the graph consists of induced matchings of size n over 4. Every time I put such a matching, I am forbidding something like close to n square over 16 edges to exist from the graph. And these induced matching, I'm tiling it up. And I'm just enforcing sparsity all over the place, right? And we foolishly even spend time trying to prove such graphs can't be very dense. But then eventually, we learned and also slightly contributed to the literature on this topic that for any constant beta between 0 and 1/4, you can create such graphs with far more edges than n polylog n. So the lower bound on the left side is not quite n to the 1.01, but it's way more than n polylog n, okay? So you can create such graphs which can have way more than linear number of edges, okay? And these constructions are delicate, and so random graphs won't have these property because induced property is not going to happen. So you have to very carefully construct such graphs. But what about the upper bound, right? That's what we really care about. The best known upper bound is n square over roughly 2 to the log star n. Okay? So log star n is, you might know, is an extremely slowly growing function. If you applied this function to maybe particles in the universe, the value will be 7, perhaps, or something. Okay, so it's extremely slowly growing. And so the upper bound is slightly better than n square, but just slightly better than n square. And it's a major open problem in graph theory and maybe all of combinatorics and discrete math to narrow the gap between these lower and upper bounds for these graphs, okay? And since the discovery of our result, the connection, that RS graphs present an obstruction to getting small space algorithms which approximate matching well, it has been refined further. And at this point, even getting a 0.59 approximation is connected to size of RS graphs. Okay, this is not a black box connection. It uses the specific known construction. So it's not the case if you improved the lower bounds on RS graphs, this bound theorem will immediately improve, whereas the 2/3 connection that we had, that's a black box connection. Okay, so there is a small modicum of positive news here as well. So last year with Sepper, Sohail Benezad, and Huan Li, we showed that this connection, which is a negative connection, on how well you can approximate matchings in small space with RS graphs, can also be used to recover something positive. That is, the known upper bounds on the size of RS graphs can also be exploited to get a streaming algorithm, which gets you close to a near optimal matching in space that is slightly or ever so slightly better than n squared. Okay, so so you can get something non-trivial. I think that's the takeaway from this this theorem. Okay, so let me wrap up with some final thoughts. So in the 1970s, when we discovered the theory of NP completeness, approximation algorithms emerged as a key tool that allowed us to deal with the intractability of NP-hard problems. Okay, these problems, exact algorithms had exponential time, but we wanted to solve them faster. And we realized if we settle for approximate solutions, we can solve them faster. So several decades of studying of these NP-hard problems, which also was from the lens of approximation algorithms, which was also my area of primary area of research in the first part of my research career, gave us really remarkable insights, not only about approximation algorithms or hardness of approximation, but I would say about computation as a whole. And we learned things which inform our understanding of computations as a whole. And one big example here is the famous PCP theorem, which came from this study of approximation algorithms and limits of approximation algorithms. But there are many techniques which emerge, which we use widely beyond approximation algorithms, structural results about flow cut gaps, embeddings, cut matching games, conjectures like unique games conjecture, which now are central objects of study by computer scientists. And last 20 years, in a parallel manner, I think, challenges of designing efficient algorithms for large data sets have done something similar. Okay, so massive data sets and efficient algorithms for that have basically shifted the challenge from of going from exponential time to polynomial time to become polynomial time to sublinear time and space. And much like the case of approximation algorithms, us revisiting these classical problems, which we knew already how to solve in polynomial time through the lens of sublinear algorithms, I would argue is also enriching our understanding of computations as a whole. Interesting new algorithmic techniques have emerged. Interesting new models of computations are coming. And we are also learning how communication complexity can inform us of limits of sublinear algorithms. So it's been an exciting journey. And there are, at Waterloo, you have big experts on this topic of sublinear algorithms. But if for some of you this was something new, I hope you are inspired to explore this topic a bit more. And that's all I wanted to say. Thank you.
Thank you, Sanjeev. I think we have time for a few questions.
Actually, I have 3 questions. Okay. 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 My general question is that I want to know for which problems we hope and we can design a subspace algorithm. For example, in matching, in matching problems, somehow the input and your output are dependent to each other. What I mean is that when you are reading the vertices and edges, you can somehow at each iteration when you read, you can check the hull condition. And whenever it is not satisfied, you can just say that we don't have any perfect matching, right?
But how do you check that you don't have space to store the entire graph?
Yes, I know, but I am saying that's optional.
Okay.
But for the problem, like you are given a matrix and you want to check if it is singular or non-singular. The inputs, the components of your inputs are independent of each other. So it's a little different for the previous problem. It is different from the matching problem. So can we hope that we can design a subspace algorithm for this kind of problems?
So even in the case of a graph problem like matching, edges can be independent of each other. So there is no dependency among the edge. And in fact, the matching problem actually can be used to get lower bounds of interest for the problem of estimating the rank of a matrix, because there are connections between rank and the matching problem. So I do not see, the matrix view as giving you somehow fundamentally easier time because the input is independent.
Yes, it makes sense. Thank you.
Other questions? I saw some other hands.
What do you think the right bound will be? What do you think the right bound is going to be on the density of the RS graphs? Like, you think it's better, closer to the lower bound or the upper bound?
It's no, I think it's I can't really make any wager. I thought you were more likely to. I thought you might ask if I thought we can get better than half in space, which is truly sublinear in n square, and because even if the RS graphs turn out to be very dense, like close to n square, no one is ruling out that 0.51 approximation couldn't happen in much better space. It's only if you wanted to go to 0.59 or something. And so I do not know. I think Sepper and I spent a little bit of time exploring, if there is some different way of thinking about RS graph density, and there's nothing I could, I would be brave enough to wager on here. And but even that basic question, can you beat half? I am a bit on the optimistic camp, but on the other hand, I've thought about it for 12, 13 years, 15 years actually now, and I've not succeeded. So maybe I should, accept there is a signal here. So.
Okay, I think in the interest of time, we'll thank Sanjeev again for a really interesting talk. And I'll remind you that there is a chance to give him ask him more questions at the reception next door in the fishbowl right now. So
thank you.
Hope to see you there. Thanks very much. That was really good. Yeah.